All right, welcome everyone to our virtual edition of Math Econ. So in this video, um, which you can thank Joey Craig for having out there, he wanted to see the general case of our constrained profit maximization problem. Now, one thing I'm going to point out, I'm actually going to solve a cost minimization problem, is to note that the way we set up the problem, I'm going to take my profits, it's a function of capital and labor, was equal to my output. Well, sorry, we've written output as Q minus capital cost minus the labor cost, subject to this constraint that I had to deliver a certain quantity of the goods, right? So I need to deliver 2,000 cement mixers, and I have to decide how to allocate capital and labor given their costs, R and W, to best maximize my profit. Now, given that Q is a constant, it doesn't in particular affect the maximization problem, right? In other words, to say I'm trying to maximize profits. Now, an important insight in control theory, or I should say sort of nonlinear programming, optimization theory, is that the maximum of the profit function is equal to the minimum of minus that function, right? So if I take the maximum of P, that would correspond to the minimum value of minus P. And so if you notice, if I take the minus P, is RK plus WL minus Q. And so what I'm effectively doing here is I'm trying to minimize the cost of producing, given that Q is just a constant, right? So since Q is a constant, my maximization problem or minimization problem is really in RK plus WL, or minus RK minus WL. That makes a lot of sense when you think of it in terms of the constrained problem. I have to deliver Q units of the good. So Q I can't choose anyway, no matter what I do. And so really, my problem is to select the K and L that delivers Q at the lowest cost. So our problem really is to pick the K and L that produces Q at the lowest possible cost. Find K and L that makes Q cement mixers at lowest cost. Right? No matter which one I use, max P or minimize minus P, I'm going to arrive at the same conclusion. So I'm actually going to, just because I think it will help you, I'm going to resolve this in the general form, doing the cost minimization. So what I'm going to solve is the following problem. I'm going to minimize, by choosing my capital and labor, my costs of production, RK plus WL, subject to the constraint that my output is equal to Q. And I'm going to use our specific production function, zk to the alpha, L to the beta equal to Q. So I think Joey was asking, without specific numbers for R, Z, K, alpha, and beta, and Q, how do we attack this problem? And so I think it's actually best solved as the cost minimization. And so one of the things I wanted to point out is that the Lagrangian technique works exactly the same, whether we're solving a minimization problem or a maximization problem. So what do I do to solve this? Is I formulate my Lagrangian, fancy L, right, which is the objective function, RK plus WL, and then minus lambda times, in this case, I'm going to do Q minus Z K of f of L. Actually, I'm going to do it this way, I think. So let me do this. Z K to the alpha, L to the beta, minus Q. Okay, and you'll see that written in this way, we're going to arrive at the same first order conditions, basically, that we did in the profit maximization. Same conditions. And we'll work out how to solve this. So the steps to solving this, I have two choice variables. Well, really, there's three values I'm trying to find. I'm trying to find capital, labor, and associated with that, there will be a value for the Lagrange multiplier. So what we do is we partially differentiate the Lagrangian with respect to k, set it equal to 0. Partially differentiate the Lagrangian with respect to labor and set it equal to 0. And I also use my constraint that total output has to be equal to Q, given those capital and labor choices. Okay, so we'll take those derivatives. We'll solve each of these equations for K and L, and we will have a solution for capital and labor, and we'll have an associated value of the Lagrange multiplier, lambda. Okay, so let's start here. Differentiate the Lagrangian with respect to K. So we've got R, right? The derivative of RK with respect to K is just R. And then I've got minus lambda times the derivative of the production function with respect to capital. That's the marginal product of capital. In this particular case, that's going to be alpha z k to the alpha minus 1, L to the beta, and that has to equal 0. So notice we're going to get the same condition there. The marginal product of capital equal to the cost of capital R. Same thing here. I partially differentiate the Lagrangian with respect to W. With respect to L. And WL, the partial derivative with respect to L, is just W. And then I have minus lambda beta times z k to the alpha L to the beta minus 1. Differentiating with respect to L. That's just my marginal product of labor. That is equal to 0. And then I also have this constraint that z k to the alpha L to the beta is equal to Q. Now, as we talked about in class, if it helps you think of it in that way, you could partially differentiate the Lagrangian with respect to lambda, and you would arrive at the constraint. Okay, I prefer just to write the constraint and have that there, and that way what we're doing is still analogous to maximizing a function, right? I'm trying to find the critical points, or the points in the Lagrangian where the derivative is equal to 0 in capital and labor. And so that condition doesn't really quite make sense when I differentiate with respect to lambda. Okay, at any rate, we now have these three equations in effectively three variables to solve: K, L, and lambda. So three equations in my three unknowns: capital, labor, and the Lagrange multiplier lambda. And I can solve these three equations for the three unknowns. So the process really here, I mean, you can attack this however you want, but it's going to work exactly the same as what we did previously. So I'm going to go ahead and solve the first equation for lambda. And I'm going to plug that value of lambda into the second equation. And we'll see we get basically the same thing. We're going to get that, with some constants times K over L is equal to W over R. I can solve that for k and plug it back into the constraint on quantity, and we'll get sort of a general solution. So the process from here is basically the same as what we did in class with specific numbers. It's just we don't have the numerical values to calculate. So what we're going to do first is I'm going to solve this first equation for lambda. So R is equal to lambda alpha z k to the alpha minus 1 L to the beta, which means that lambda is equal to R over alpha z k to the alpha minus 1 L to the beta, where remember, that's just R over the marginal product of capital. That term on the bottom is the marginal product of capital. All right, so then I can plug that value of lambda into my other first order condition. So we know that W is equal to lambda times beta z k to the alpha L to the beta minus 1. And so let me plug in for lambda that we've just derived. So W is equal to R over alpha z k to the alpha minus 1 L to the beta. That's lambda. And then it's times beta z k to the alpha L to the beta minus 1. So it looks pretty hairy at first, but we're going to get a lot of nice cancelizations here, right? So first, notice the z's are going to cancel. So I have z over z. And if I kind of put all the constants together, then what we have here is we have R beta over alpha times k to the alpha L to the beta minus 1 over k to the alpha minus 1 L to the beta. Now, if you simplify this part, it's just going to knock out to k over L, right? So if we have k over alpha, k alpha minus 1, is k to the alpha minus alpha minus 1, which is just k to the alpha minus alpha plus 1, which is just k to the 1. So we've just got k. When we take the L to the beta part, L to the beta minus 1, let me just make that k to the 1 a little bit better, or L to the beta, L to the beta minus 1 minus beta, which is L to the minus 1, which is 1 over L. So when I simplify that, I have now W is equal to R beta over alpha, k over L. And notice that's exactly the same thing that we had before, right? So when I divide the R over, so what we have is W over R times, if we want, alpha over beta is equal to k over L. So again, same conclusion, that the capital to labor ratio is a fixed constant of the relative price of capital and labor, W over R. Okay, so now, with this, I could solve for k as a function of L. So k is equal to W over R, alpha over beta, times L. I can then plug that into my constraint, which is a function of capital and labor and everything else. And then I can use that to solve for L, right? So what do we have? So then I plug that into my constraint, which was my third equation. Z k to the alpha, L to the beta is equal to Q. So I can just plug k into here. And what I have is that Z times I'm going to just combine this W alpha over R beta to the alpha power times L. That's K to the alpha. Times L to the beta is equal to Q. Now I can just combine the L terms there and solve for L. So I have, in and amongst all of this stuff here, we have, if I'll leave it like this for a second. So we have Z times W alpha over R beta to the alpha times L to the alpha plus beta. All right, so I'm just adding those two constants together. And that has to equal Q. And I can now do some dividing, and I can start to find the solution for L. So L to the alpha plus beta has to be equal to Q divided by Z, and then it's going to be divided by, you can do this however you want, but that's going to be R beta over W alpha to the alpha. And then I'm going to take that whole thing on the right-hand side to the power 1 over alpha plus beta. So now I have to take the root of both sides. And we then have L is equal to Q over Z, R beta, W alpha to the alpha, all to the 1 over alpha plus beta. So fairly big mess, but the solution method is fairly straightforward. And I think it's a good point, right, that if I solve this in the general form, then you give me the numbers and I can plug them into my formula and give you a numerical answer. So a lot of times that's what I'll do, right? If I'm going to use this problem a fair amount, I'll arrive at this general solution, and then I can use that as we change the parameters and see what happens. So then with L, I could plug that back in here and obtain the value of K. So K is going to be equal to W alpha over R beta times this whole thing. Q over Z, R beta, W alpha, the alpha, that whole thing to that power. And of course, I've got this term in there, the W alpha over R beta, which I could simplify that and combine the terms, but I'll just leave it at that for now, and we have a solution for K and L. And given those solutions, we could plug it into this form. If we wanted to, and find the specific value of the Lagrange multiplier, which in one of the other videos we will actually take a look at, as that value can be interesting. So there we go. If you can handle that problem, you can pretty much handle any problem in a first-year graduate program in economics that we could reasonably throw at you in terms of constrained optimization. So give that a try. Takes practice. You want to try it on your own several times until you can kind of consistently solve the problem. And if you do that with enough practice, pretty soon you won't have to think about it, and you should arrive at the correct solution. All right. So if you're still there and you haven't either fallen asleep or destroyed your computer and rethought your life choices, thank you for listening and watching, and I will see you in another video.